In this lesson, you'll learn to find the maximum and minimum values of a function over a region and solve real-world problems using linear programming. How is linear programming used in scheduling work? One of the primary tasks of the U.S. Coast Guard is to maintain the buoys that ships use to navigate. The ships that service buoys are called buoy tenders. Suppose a certain buoy tender can carry up to 8 replacement buoys. Their crew can check and repair a buoy in 1 hour. It takes the crew 2.5 hours to replace a buoy. The buoy tender captain can use a system of inequalities to represent the limitations of time and the number of replacement buoys on the ship. If these inequalities are graphed, all points in the intersection are the combinations of repairs and replacements that a buoy tender can schedule. The inequalities are called the constraints. The intersection of the graphs is called the feasible region. When the graph of a system of constraints is a polygonal region like the one graphed to the right, we say the region is bounded. Sometimes it is necessary to find the maximum or minimum values that a linear function has for the points in the feasible region. For example, the buoy tender captain wishes to maximize the total number of buoys serviced. The maximum or minimum value of the related function always occurs at one of the vertices of the feasible region. Graph the following system of inequalities, name the coordinates of the vertices of the feasible region, find the maximum and minimum values of the function f of xy equals 3x minus 2y for this region. Okay, so we've got 1, 2, 3 parts to this one problem. So first things first, let's get the graph. X equals 5 is 5 units to the right, vertical line, and the boundary is included, so it's a solid line. Y equals 4, 4 units up, all the values for y equals 4 is a horizontal line. And the orthogonal line, x plus y is greater than or equal to 2, would have a y-intercept at 2 and an x-intercept at 2, and we could draw that line. And they're all solid lines because they're all or equal to. Okay, the first two, it's easy to see the shading because it is less than the x equals 5 and less than the y equals 4. Now, on the orthogonal line, it would have been nice if we had solved that line for y. Then I can be sure it's shade above the line, and then I could have graphed it with a y-intercept of 2 and a slope of -1 as well. The vertices are where our lines cross. So we've got vertices at -2, 4, 5, 4, and 5, -3. The last thing they asked us to do was to find the maximum and minimum values of the function. So we're going to put our ordered pairs into this weird looking function that's f of xy. They're giving us a rule for both x and y. So we have 3 times -2 minus 2 times 4. -6 minus 8 is -14. 3 times 5 minus 2 times 4. 15 minus 8 is 7. And 3 times 5 minus 2 times -3. 15 plus 6 is 21. So our maximum value is the largest. It's 21 at 5, -3. Our minimum value is -14 at -2, 4. The notation f of xy is used to represent a function with two variables x and y, as read f of xy. That system was bounded, it had boundaries all the way around the feasible region. Sometimes a system of inequalities forms a region that is open. In this case, the region is said to be unbounded. Graph the following system of inequalities. Name the coordinates of the vertices of the feasible region. Find the maximum and minimum values of the function f of xy equals 2x with 3y. I think for graphing we like to solve for y first. So I'm going to take the first equation and add x to both sides, so 2y is less than or equal to x plus 2, and divide by 2, so y is less than or equal to 1/2 x plus 1. The second equation, subtract x from both sides, and I have negative 2y is less than or equal to negative x plus 4. Divide by negative 2, and y is greater than or equal to, we divided by a negative, we need to reverse our inequality, 1/2 x minus 2. And the third equation, they saved the best for last. All we have to do is subtract x from both sides, and we're ready to graph. The first equation had a y-intercept at 1, and the slope was going up 1 over 2. The second equation had a y-intercept at negative 2, and its slope was going up 1 over 2 as well, parallel lines. And the third equation had a y-intercept at negative 2 as well, but its slope was going down 1 over 1. So this is an unbounded region, so I only get 2 vertices. When I substitute in negative 2 for x, we're going to have 2 times negative 2 plus 3 times 0 for y. So we get negative 4 and 0 for x, negative 2 for y. We get negative 6. So our minimum value is negative 6 at 0, negative 2, and this is not going to have a maximum value because the region keeps going and going and going. You cannot just assume that the lowest value on the graph will be the minimum or the highest will be the maximum. Always test a point contained in the feasible region when the graph is unbounded. We tested 2 points and we found the lowest we could go was negative 6. The process of finding maximum or minimum values of a function for a region defined by inequalities is called linear programming. The steps to use to solve a problem using linear programming are listed below. First step, define the variables. Second, write a system of inequalities. Third, graph the system of inequalities. Fourth, find the coordinates of the vertices of the feasible region. Fifth, write a function to be maximized or minimized. Sixth, substitute the coordinates of the vertices into the function. And seventh, select the greatest or least result. Answer the problem. Linear programming can be used to solve many types of real-world problems. These problems have certain restrictions placed on the variables, and some of the functions of the variable must be maximized or minimized. A landscaping company has crews who mow lawns and prune shrubbery. The company schedules 1 hour for mowing jobs and 3 hours for pruning jobs. Each crew is scheduled for no more than 2 pruning jobs per day. Each crew's schedule is set up for a maximum of 9 hours per day. On an average, the charge for mowing a lawn is $40 and the charge for pruning shrubbery is $120. Find a combination of mowing lawns and pruning shrubs that will maximize the income the company receives per day from one of its crews. Okay, the first step is to define the variables. So let's let M be mowing jobs and P be pruning jobs. Now the obvious constraint we can do first is we cannot have a negative number of jobs. So both M and P need to be greater than or equal to 0. The time constraints will give us one equation. They said that each mowing job takes 1 hour. So we can have 1 times the number of mowing jobs. And pruning jobs take 3 hours, so 3 times the number of pruning jobs. And the most they want to work is 9 hours a day. They also said that each crew is scheduled for no more than 2 pruning jobs a day, so P has to be less than or equal to 2. Now, in this situation, one is not necessarily the independent variable and the other one the dependent variable, but they just went ahead and assigned M to the horizontal axis and P to the vertical, which is fine. So we've got M is greater than or equal to 0, and shade above. P is greater than or equal to 0, shade to the right. And then our orthogonal line, if we solve that for P, since that's where our vertical axis is, we'd have 3P is less than or equal to 9 minus M, divided by 3, switch my order here so it's how we like it. So negative 1/3 m plus 3. So we have a y-intercept at 3, and our slope is going down 1/3. And again, it is shaded below. So there's our blue shaded region. Our vertices are at 0, 2, 3, 2, 0, 0, and 9, 0. The word problem describes the function as, I'm going to write f of MP equals, they're going to get $40 for mowing plus $120 for pruning. If we evaluate the function for our 4 vertices, we can find our maximum and minimum. I guess we really don't care about minimizing. We'd like to maximize this time. So 40 times 0 plus 120 times 2 would be 240. 0 plus 0 is 0. 40 times 9 plus 120 times 0 would be 360. And 40 times 3 plus 120 times 2, 120 plus 240 would also be 360. So 2 of our vertices give the same maximum. So now you're getting into human relations. 9 mowings and no prunings will get you as much money as 3 mowings and 2 prunings. I'm guessing at some point people are going to want the pruning done, so some days you're going to have to go this route. The maximum and minimum values of a function are determined by linear programming techniques.